Okay. So, again, I'm Eva Maria Vecchi. I'm presenting on behalf of Tamara, Luana, and Steve, who unfortunately couldn't make it today. Just to put you in the framework of what we're going to be talking about, we're going to focus on compositional distributional semantics, which of course is a big topic going on in the field of computational semantics right now. And of course, in compositional distributional semantics, our goal is to represent the meaning of a phrase or a sentence as a single structure. And a phrase is represented as a functional composition of the semantics of its constituents. And in our case, or in this case, we want to focus on the structure representing a sentence and have it be a single vector in a predefined semantic space. For example, here we can generalize the meaning of the sentence, the cat sat on the mat, by looking at, of course, the content words, just sat, the cat sat, and mat. And we can somehow compose the representation, for example, the vectors of the nouns mat and cat, and a representation for the verb, and what that representation will be, I'll go into more detail later, in order to generate a single representation for the full subject-verb-object sentence. Okay? So we could go ahead and do it simply, like has been done previously, where we can go ahead and do just some sort of simple component-wise function, like addition or point-wise multiplication. But of course, this is nice for obvious reasons. It's simple. You don't need any training, and it's pretty direct. And it's actually shown to be quite successful in a number of tasks. But the obvious downside is that it's not sensitive to word order, which of course is very important in a situation of subject-verb-object, right? So in the case before, if we have the cat sat on the mat or the mat sat on the cat, those are obviously two very different sentences, right? And one we really don't want to represent because that's just weird. In this formalism that I'll be presenting today, we're going to go ahead and have two separate types. We're going to have atomic types, such as nouns and so on, which can be represented as vectors. And then we're going to have function types, which are, for example, verbs, or we can even consider adjectives or adverbs to be function types. And these will be represented as tensors. And so in a sentence consisting of a subject-verb-object, we can have k-dimensional vectors representing the subject and object, nouns, and we can have an s by k dimensional tensor representing the verb. And of course, just to give a quick overview of what we mean by distributional vector, hopefully many people know about this now, but if you don't, we can represent the meaning of a word like cat or tiger or so on with respect to its distribution in text. So we can go ahead and consider the co-occurrences with its content words in a text, or context words in a text, and we can go ahead and represent it as a multidimensional vector with respect to these co-occurrences or distribution with these context words. So just a quick overview. I'll go ahead and introduce the type-driven framework, and then I'll introduce the plausibility task that was used to evaluate this framework. And of course, I'll go ahead and get into the experiments and the results, the fun part. So first, type-driven composition. What do I mean by that? So on the left, you can go ahead and see that we have a traditional parse tree. And on the right, we have the CCG equivalent, right? I hope some of you are familiar with this notation. And if you're not, don't worry. We'll get into prettier pictures later, so you don't have to know everything. But if you do know about this and are able to follow it quite well, what we can do, which let me introduce very quickly this, we can go ahead and treat function words, like I mentioned, the tensor, so nouns, or sorry, adjectives or verbs or so on, as functions. And a really simple example of this would be something like red car, where we could go ahead and treat red as a function which maps car to red car, right? And it's very similar to it is based on the work of Baroni and Zamperelli, of course, of 4 years ago. And of course, this is just an example to show the notation. We can go ahead and represent it as so, where it's just tensor product, and just so you can see that there are two indices, of course, to specify the product in the matrices, just so you can generalize quite simply. So for transitive verbs, this formalism extends to multilinear algebra to represent functions that have two inputs as tensors. So it's pretty simple to go from syntax to semantics in this formalism. So pretty much you just replace the slash in the CCG framework to the tensor product. And of course, you just go to 3 indices to represent the cuboid. And of course, we can see how the CCG derivation works very well in parallel to the tensor contraction. And like in the adjective noun framework, function application, so applying the object noun to the function chases, is equivalent to taking the inner product. So this is considered tensor contraction. And again, this is a product, and you can see quite easily how it will work. And of course, you can continue the multiplication. So once you do the object with the verb dog with chases, you can, of course, then go ahead and apply, cat with chases, then you go ahead and apply, I'm saying it the other way, dog with chases, you can go ahead and apply cat with chases, and you can get the sentence space. But of course, there's a couple things to consider when you're going from theory to implementation. And of course, the big thing is that it leaves a couple unanswered questions. So first of all, what is the sentence space that we're talking about? I've mentioned it a couple times, but I haven't really defined it quite yet. And of course, how do we learn the tensors? That's a pretty big question. And of course, the problem can get quite complex because the tensors can get very large. For example, a simple preposition like in, which is seen quite often, can become quite complex. So I'm just going to introduce very quickly the plausibility task before I get into the discussion of how we're going to go ahead and train and define our sentence space. So the motivation for working in a plausibility task is quite simple. First of all, it's a simple sentence space that we'll be working in, which I'll talk about. And it's also very easily implemented in something like language modeling. So just a couple examples to give you an idea of the type of sentences that we'll be working with. So imagine 2 types of categories, positive examples and negative examples. And in positive examples, you can imagine something like court applies law. And an implausible sentence would be something like plan applies title. And you can see these in our examples. The data set of verbs that was chosen was a set of 10 verbs with varying concreteness. And they generalized the plausibility triplets by finding them in the Google N-gram corpus. Some verbs were actually quite rare in their transitive form, while others occurred in thousands of triples. They limited the number of triples to the 2,000 most frequent. Okay. And of course, here's an example of some of the training data. The negative triples were generated to replace the nouns with random nouns in a similar frequency range as the original nouns. So you're able to easily do a binary classification of plausibility, which I'll go ahead and discuss in a minute. So how do we learn the tensors? This is the fun part. Well, first of all, we can build the noun vectors, which are the atomic types, and those are, of course, quite easy to build. We can go ahead from the Wikipedia corpus, build vectors for all the nouns using the top 10,000 most frequent lemmas as context, and use a co-occurrence window of a sentence-like window, and they transform the raw co-occurrence counts using t-test weighting, and then applied context selection and normalization techniques from their EACL paper to produce high quality and low dimensional vectors. Just to give you an example, I hope that you can see it, but if not, I'll go ahead and explain. It's an example that gives you a quick demonstration of how these techniques improve the low dimensional SVD vectors. If we look at the 20 topics of a regular SVD, we can see how many of the topics are incoherent and share the same top words. With context selection and normalization, we actually get a nicer, coherent set of topics, which are much easier to interpret. Just so you know, these topics were selected from the MEN data set, which was about 7,500 words. And yes. So, just to give you a quick introduction of our notation. I'm not going to continue to stick with the CCG notation because I know that sometimes it takes some people a while to turn their mind into that notation. So just to give you an easier way of looking at it, this is a slightly nicer representation of the architecture, in which you can see there's a k-dimensional noun vectors for the subject and object, and they're multiplied with the verb tensor to produce a two-dimensional plausibility space, and we are able to produce this two-dimensional plausibility space using softmax. And so the idea here is if the subject noun and the verb nouns are k-dimensional vectors, and the plausibility space is an s-dimensional space with s equal to 2, of course, we can learn the values of the k by s tensor by representing the verb of the parameters, verb as parameters of a regression algorithm. To represent the space as a distribution over two classes, obviously true or false, we can apply a sigmoid function to restrict the output to the 0 or 1 range, and the softmax activation function, g, to balance the class probabilities. The full parameter set, which needs to be optimized for, is b, where b is equal to v and theta, and in this case, theta is true or false. Theta equal to true or false are the softmax parameters. So it's quite easy to do a binary classification based on this. So for training, they use the cross-validation for training and testing. They minimize the KL divergence between the gold standard distribution for each training example and the predicted distribution, and they optimize using AdaGrad. So I'm going to go into a bit of a description of the various types of tensor functions that they apply, in which they test in their evaluation to compare. So the first one is the two-mat, the two-matrix, and this is an alternative approach to the original, just the simple tensor contraction before. And in this approach, you can decouple the interaction between the object and the subject by learning a pair of S by K matrices for each of the input noun vectors. The resulting S vectors are concatenated after the subject and object nouns have been combined with their matrices, and combined, of course, with the softmax component to produce the output distribution. A third option is the SK-mat, which is an option for generating a sentence vector with, again, 2 dimensions. And in this framework, we consider the verb as an S by K matrix, and we transform the object vector into a K by K matrix with the noun on the diagonal and zeros elsewhere. And we can combine the verb and object to produce a new S by K matrix, which is encoding the meaning of the verb phrase. We then complete the sentence reduction by multiplying the subject vector with the verb phrase vector to produce an S-dimensional sentence space, again, S being 2, using softmax. Next, we have the noun by noun space matrix. In this framework, in this framework, it's learned in the same way as in the previous matrices, but instead of using a softmax classifier, we use a logistic classifier with mean squared error. So given a two-class problem, such as plausibility, true or false, classification, the softmax implementation is over-parameterized because the class membership can be estimated with a single value. Okay. And then finally, the noun by noun distributional matrix. This is just the baseline. It's a corpus counting framework in which we can sum the outer product of all plausible subjects and objects divided by the number of plausible pairs. Okay. So, some results. This is quite a lot to look at, and I understand that, but there are a couple take-home messages here. The first is that, of course, we find that, what performs best? Well, we find that the KK-mat and the 2-mat perform better than the tensor, while the SK-mat performs worse than the baseline, which is a shame. But the main take-home message is that matrices do well, just as well as tensors, which is quite important. And they're good at learning. And the verbs, in an error analysis that they did, the verbs that they found that were actually performing poorly were those that were quite rare and had very few training examples. And so they can go ahead and credit this to them likely selecting less strongly with respect to selectional preference. So just quick conclusion. So our results indicate that, or their results indicate that we can use a small number of dimensions to learn good quality vectors. Smaller representations can adequately replace tensors for certain tasks. And of course, there's some further work, such as other architectures for learning, learning sentence spaces for other tasks, like similarity, sentiment analysis, and so on, and integrating the semantics into a CCG parser. Thank you. These are the authors.
We have plenty of time for questions.
Hi, Eva.
Hi. Be nice. That's not my work.
Oh, yes. Can we ask questions, actually? Are you okay? I was just wondering, in the slide before the conclusions, what is the task?
So the task is the binary classification, or in the one tensor framework, just the selection of plausibilities. So whether, yeah. So people eat food or work eat variety. So to go ahead and classify people eat food as a plausible, and work eat variety as an implausible sentence.
Right, okay, I was late, so I didn't see this first slide. Right, okay.
So it's a F-score measure. Actually, in the paper, they actually explore other types of measures to evaluate the frameworks. So I would encourage you to look into how they, I think they look into AUC as well.
Okay, thank you.
More questions? So one question I have is a couple of questions actually. So one baseline that I can imagine is just training a language model,
Right.
and just training a classifier based on that.
Right. I don't think that they have experimented with that, but that does seem like a simple thing. But I don't want to say that it's equivalent to this, but it would be quite similar to the baseline that they used, right? I would expect the results to be quite similar because it is parallel.
The other question, so you showed this complex CCG category for the preposition. So this work doesn't address that at all, or does it, or no?
No, but the idea, sorry, let me go to that so everybody can see. So the idea behind it is that if we can go ahead and implement things in a reduced space and in a simple training method, without needing, k dimensions being something quite absurd, then eventually we would be able to handle something like such prepositions, right? It wasn't something that they experimented with yet, but if it's something that is computationally feasible with reducing space and reducing dimensions, then it's something that can be tackled.
Mm-hmm. Cool. So is the future direction basically trying to get this kind of representations into the parser? The
Yes.
CCG? Okay.
So that they're really interested in trying to implement this in the CCG parsing.
Mm-hmm. Still have some time for questions.
Hi, Eva.
Hi.
Thanks for presenting work that's not your own. I was wondering, do you happen to know if they looked at all at Alessandro Lenci's ECU model, because it's about the thematic fit of arguments with the verb, and if they haven't or maybe even thinking of doing it, I would be interested in seeing if there's a difference whether or not you integrate the subject first or the object first.
I know that they did play around with, in a couple of models, there is, of course, it's order sensitive, not of course just word order sensitive, but order of function application sensitive. And I know that they did play around with it. I don't know if in the paper they do present any results with respect to improvement when implementing first the subject or first the object. But I do know that they looked into it, and I'm sure that if you write to them, they would have some results with respect to that.
More questions?
Yay, Manoush.
Just to kill time. Do you know if they experimented with a disambiguation task with the verb matrices?
So to disambiguate using the verb matrix, I don't know about any work that they have done on that.
Okay.